Alright, so today we're going to go over E2.5, which is transformations of functions. Before we can start transforming functions, we need to know what their original shape is. Okay, so we have several functions that you need to be aware of their original shape, and we call them the parent functions. Okay, so these are just the basic shapes we need to know so that we can transform these functions. Okay. And when I say transform, what we're going to be doing is taking a function and moving it up, down, left, right, reflecting it, stretching it, shrinking it. Okay, we're just going to do all kinds of crazy stuff to it. But in order to get a good picture, we need to know what our original function looked like. So there's 7 that I'm going to go over. The first one is a constant function, which looks something like f of x equals c. So it's just y equals some number. Okay, so if I were to graph that, that would just be a straight line, something like this. Okay, here I'm graphing y equals 3, but c could be positive or negative. Either way, it's just going to be a straight horizontal line through whatever c value we have, which means that our domain, notice it keeps going in both directions, is going to be negative infinity to positive infinity. Okay, and our range, if I look as far south as I can go and as far north as I can go, the only y value I have is that one y value, whatever that c value is. So since there's only one value it can take on, I'm going to use the squiggly brackets, the set notation, and just say the range, the only y value we can have is c. Okay. The identity function looks like f of x equals x. Okay. So whatever I put in, I get out. So if I wanted to make an xy table, and you don't have to do this, but I just want to show you. If I plug in like -2, I'm going to get out -2. If I plug in 0, I'm going to get out 0. If I plug in 3, I'm going to get out 3. Okay, whatever I plug in, I get out. That's why we call it the identity function. So notice if I wanted to graph these, go ahead and put my dots on here. 1, 2, 3, 1, 2, 3. This is just going to be a straight line through the origin, headed in the positive direction. Okay, any straight line other than horizontal and vertical lines keep going both left and right and north and south, which means that my domain on this function would be negative infinity to infinity, and my range would be negative infinity to infinity. Okay, let's look at another one. This next one is quadratic function, which we should know what quadratic function shapes look like. This is just f of x equals x squared. This is the most basic form of a quadratic. Again, we should know that it makes a parabola, but if you want to make a little xy table just to make sure, if I plug in -2, 0, and 2, when I plug them in, all I do is square them, which gives me 4, 0, 4. So at -2, I'm up at 4. At 0, I'm at 0, and at +2, I'm up at 4. So if I connect my dots, this is just a nice little parabola through the origin. Okay, so the domain of this parabola, like all parabolas, is negative infinity to positive infinity, and my range is going to be from 0 up to infinity. Okay. Same thing with a cubic. A cubic function looks like f of x is equal to x cubed. Okay. If we're not sure about that, again, we can make a little xy table. I'm going to plug in several numbers since we haven't seen this one before. I'll plug in -2, -1, 0, 1, and 2. When I plug these numbers in, all I'm going to do is cube them. -2 cubed gives me -8. -1 cubed gives me -1. 0 cubed gives me 0. 1 cubed gives me 1. And 2 cubed gives me 8. Okay, so at -2, I'm down at 1, 2, 3, 4, 5, 6, 7, 8. At -1, I'm at -1. At 0, I'm at 0. At 1, I'm at +1. And at 2, I'm up at 8. 2, 3, 4, 5, 6, 7, 8. Right there. Okay, so notice if I connect my dots, it has a little jog over in the middle. It makes a little whoosh kind of shape. Okay, cubics always make this shape where they start up on one side and kind of jog over in the middle. Okay, the little jog over tells you where the absolute middle of this function is. Notice it has arrows, so it's going to keep going in both directions, both north and south and left and right, which means that both my domain and range for this function would be negative infinity to infinity because it keeps going in all directions. Okay, let's look at another one. If we look at the square root function, okay, that looks exactly about how we'd expect it. F of x is equal to the square root of x. Okay, now notice on square roots we can't plug in negatives, right? Because if we plug in a negative, we get an imaginary number or an I, and we can't graph those on the rectangular coordinate system. So the first possible thing that I could plug into a square root would be 0. So I'm going to go over here and just make a little XY table. I'm going to plug in 0, 1, 4, and 9. Obviously I want to plug in things that are perfect squares so we don't get decimals. So the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. Okay, so I'm just going to plot these. I have 0, 0, 1, 1, 4, 2, excuse me, and 9, 3. So notice when I connect my dots here, my original dot, my 0, 0, does not have an arrow on it, remember, because we can't plug in negative numbers, so it can't go any further to the left. So that just stays a solid dot, and I draw my arrow out to the other side, which means that my domain value starts at 0, I'm including it with a bracket, and then it shoots out to positive infinity. The same thing is true with my range. My lowest y value here is 0. My highest y value, that arrow says it's going to keep going up, so positive infinity. Okay. Then I look at my cube root function. So I have f of x is the cube root of x. Now with cube roots, we don't have to worry about negatives. We can plug in negatives, 0, and positives. So I'm going to go ahead and just make an xy table. And I'm going to plug in things that are perfect cubes, like negative 8, negative 1, 0, 1, and 8. The cube root of negative 8 is negative 2. The cube root of negative 1 is negative 1. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of 8 is positive 2. So I'm going to go ahead and plot these. At negative 8, I'm down at negative 2. Okay. At negative 1, I'm at negative 1. 0, I'm at 0. Positive 1, I'm at positive 1. And out at 8, I'm up at positive 2. Okay. So notice this one also makes the little whoosh, but my whoosh is sideways. Okay, so that's a good way to remember the general shape. When you have a cubic, then the whoosh is going up and down. When you have a cube root, the whoosh is going sideways. Okay. All right, domain and range, just like my other whoosh, is going to be negative infinity to positive infinity because it keeps going left and right, keeps going north and south. Okay. All right, let's look at one more, which is our absolute value function, which is f of x is equal to the absolute value of x. Remember, absolute value just makes everything positive. Whatever you put into an absolute value comes out positive, whether it begins as a negative or a positive. So again, I'm just going to make a little xy table. If I plug in negative 2, 0, and 2, all those come out positive. So I get 2, 0, 2. So at negative 2, I'm up at positive 2. 0, I'm at 0. 2, I'm at 2. So notice this just makes a nice V shape. Okay. And my domain of a nice V shape is going to be negative infinity to infinity because it keeps going left and right. My range, my lowest y value is 0, and then it's going to keep going on up to positive infinity. Okay. So these are the basic shapes that we need to know. Whenever we transform functions, if we transform an absolute value, you need to know, okay, the original function started with a V, okay, and have your points for that. The other thing we need to be really good at is being able to tell which variable is being affected. Is it the inside variable or the outside variable? Okay, is it the x or the y? When it's written in function notation, remember f of x is equal to y. It's the same as our output. So that means anything being done to the y variable happens outside the parentheses. Okay, Same thing is true with the x. The x is inside the function. I always plug in x. X is our input. So anything being done to the x variable happens inside the parentheses. Anything being done to the x variable happens inside the parentheses. Okay. All right. So now that we know what our basic shapes look like, and now we know where to look to see if something's happening to y or something's happening to x, now we're going to actually go over the different types of transformations we can have. Okay. Now, here it says let f of x be a function whose graph is known. So that's one of our parent functions or a picture they give us. Okay, c is a constant, which means it's just any number. And assume g of x is going to be our new function. Okay, once we transform it, we can't still call it f of x because if we've changed it, it's a new function. So for vertical shifting, that means I'm moving my picture up and down vertically. If I'm moving things up and down vertically, that should be affecting the y variable because the y variable is the vertical axis. Okay, anything being done to the y happens outside the function. So if I want to move my graph a shift c units upward, that means I'm going to take my y, which remember is f of x, and I'm going to add c to it. Okay, notice I'm adding the c outside the parentheses because it's happening to the y. Same thing if I want to move c units downward. Okay, I take f of x and I subtract c, which means I go c units down. Okay, both add and subtraction of c here is happening outside the parentheses because it affects the y. Okay. Now I want to look at horizontal shifting. For horizontal shifting, when I go left and right, that's going to affect the x variable because the x is the horizontal axis. Okay, so I'm going to be adding and subtracting c inside the parentheses. Okay, now the thing with x's is they're backwards from what we would think. I'm going to show you an example in just a second. But here, if I want to go c units to the right, in our minds we would think we would add c, but actually inside the parentheses we subtract c. Okay, to go c units to the left, we would think we should subtract, but here we actually add c inside the function. Inside the function because it's affecting the x. Okay, so for an example, let's just look at like x squared. Okay, x squared we know makes a little parabola, right? If I wanted to do, say, x plus 3 quantity squared, if I wanted to make an xy table for this, remember when we were going over quadratics, we can find the vertex here. The x value of the vertex is the value that makes inside the squared quantity 0. So that's the absolute middle, which here would be x would have to be -3. So I could plug in -4, -3, -2. If I plug in -4, -4 plus 3 is -1, squared, I get 1. When I plug in -3, -3 plus 3 gives me 0, which when I square it is still 0. And when I plug in -2 plus 3 is 1, which when I square it gives me 1. So notice if I wanted to graph this, it's actually going to end up over here to the left, right? Over here at -3 is going to be my center point, and we're going to get something that looks like this. Okay, so even though inside the parentheses we were adding 3, what it did to my picture is it moved it to the left 3. And the reason that is because our vertex is always located at the value of x that makes inside that squared quantity 0. So here, since I have x plus 3, it's a -3 is going to be my axis of symmetry, or that center line point, which moves it to the left. Okay, so if we can just remember our x's are backwards from what we would think. So I'm just going to put over here, x's are, let's see, that's not going to fit very good. X's are backwards of what we think. Okay, so if we can just remember anything that affects the x is a little bit cattywampus, so to speak, or a little bit different than what we would hope it would be. Okay, if we can remember x's are backwards, it's a good indicator that you're doing it correctly. Okay, so now we know how to move the picture up and down, we know how to move it left and right. Now we want to look at reflections. Okay, to look at reflections, that means we're using one of the axes, either the x-axis or the y-axis, to copy the picture across it. Okay, so here it says reflection with respect to the x-axis. So I'm just going to draw a picture over here to help us. Let's say we have the square root function. If I want to reflect this across the x-axis, so here's my x-axis, that means I end up with something like this down here. Okay, so notice going from my straight line to my dotted line, if I flip things down, okay, from being up here to being down here, my variable is changing, one of them. Notice all my x values are the same. Here my y's are going from up here being positive to down here being negative. So notice what's happening is my y's are being negated. Okay, or we're changing the signs of the y's. So in order to have a reflection with respect to the x-axis, my function needs to negate the y's. So the y's are outside the function, so I'm going to put my negative before the f of x, okay, not inside the function. The same thing is true with reflection to the y-axis. If I wanted to use the same picture, okay, I have a little half parabola, my square root function. My y-axis, remember, is my vertical axis. So if I reflect it across the y, now it's going to look something like this. Okay? If I reflect it to that side, notice what's happening is my x's are changing sign. All my x's were positive over on the right quadrant, and then when I flip it over to the left quadrant, now my x's are negative. So to flip it across the y-axis, now I'm going to negate the x's. So here the x's are being negated. Okay, so to negate the x's, that happens inside the function. So this would look like f of negative x. Okay, so it's important to know whichever variable it's affecting, where that operation needs to happen, inside the function or outside. Okay, another good way to remember this one is whichever axis you're flipping it across, it negates the opposite variable. So if I want to flip it across the x-axis, I negate my y's. If I want to flip it across my y-axis, I negate my x's. Okay. And then the last one we have is stretching and compressing. Vertical stretching. Okay, vertical affects the y, so this is going to happen outside the function. And the way that I can stretch it is by multiplying by a number. So I'm going to do some number c times my y's, my f of x's. Okay, the same thing is true in order to get vertical compressing. I still am multiplying by a number. Now, to determine whether it's stretching or compressing, it depends on what type of number I'm multiplying by. To get a vertical stretch, I have to multiply by a large number, okay, or a number larger than 1. So if I multiply by 2, 3, 4, 4.5, okay, that kind of thing, that's going to make my picture bigger because I'm increasing each y. If I want to compress my picture vertically, then I need to multiply by a small number, namely a fraction, right? If I multiply everything by 1/2, it's going to make all my y values half of what they used to be, which is going to make it smaller. Okay, so if I multiply by a fraction, it compresses it. If I multiply by a number larger than 1, it's going to stretch it. Okay, so that makes sense, right, for the y's. Now for the x's, remember, it's completely backwards of what we would think. Here, in order to stretch and compress, I still use multiplication, and because it's happening to the x, the multiplication takes place inside my function. Okay, so here I'm going to multiply by c on the inside of my function, but remember, it's backwards from what we would think. So in order to stretch it, we would think we need to multiply by a big number when actually we need to multiply by a small number. Okay, same thing with horizontal compressing. In order to shrink it down, we would think we need to multiply by a small number, but with x's being backwards, we actually need to multiply by a number larger than 1. Okay, so last thing I need to go over before we do some examples is the order of transformations. This is kind of like the order of operations. Remember, please excuse my dear Aunt Sally or PEMDAS. This is the same thing, but it's the order we have to do our transformations in. You may have all your transformations correct, but if you do them in the wrong order, your picture isn't going to look right. Okay, so the order here, our acronym is HSRV. We do horizontal first, then stretching and compressing, then our reflections, and then last we do our vertical shifts. Okay, if you need an acronym or whatever to help you remember it, you can just remember HSRV. The way I learned it was high school RV. That doesn't really make any sense, but that's how I was taught it. I've also learned, let's see, Heath, salute, returned, veterans, and we've also heard that having sex reduces virgins. Okay, so anyways, you can come up with your own as long as you can remember that it has to be done in the order HSRV. Okay, that's the big important thing. So if you're a super phenomenal note taker, this is something that you definitely want to remember. Okay, all right, let's go ahead and look at an example. Now, before we get into these, I'm going to be very particular on how I grade these. I teach it a very specific way to make sure you understand each step of the transformation. I do understand that you could just make an XY table and get the correct picture, but that's not how I'm teaching you to do it, so that's not how I'm going to grade it. I do want you to be able to identify the parent and the end result, but I'm grading you on can you take a function written in ordered pairs and modify those ordered pairs for each transformation step to end up with your final picture. Okay? So let me show you how I'm going to do it. That way you'll know how you're going to be graded on your worksheet and also your exam. Okay. All right. So the first thing I need to do is identify the parent function. When I identify the parent function, I'm looking for the most basic form of this function before anything got done to it. So here I notice I have a quantity being squared, which means that my parent function had to have been x squared. So I'm going to go down here and I'm going to go ahead and make a table of values for x squared, and then we'll modify it for each transformation. So my original x squared should be a parabola. So I'm just going to plug in a few points that I know will give me a nice parabola, like -2, 0, and 2. When I plug in -2 and squared, I get 4. When I plug in 0, I get 0. When I plug in 2, I get 4. So I'm going to go ahead and graph my original parent function. On your worksheet, you don't have to graph the original. I just want the end result. You can if you want, but I'm going to do it just so we can see what happened. Okay, so this means at -2, I'm up at 4. At 0, I'm at 0. And at +2, I'm up at 4. So this is just the original parent function, just like we went over at the beginning of class. Okay. So this is our x squared. Now I want to go ahead and modify it, seeing what transformations happened. The only thing that has changed this from being a regular x squared to the function it is now is that I have this subtraction of 2 inside the function. If it's happening inside the function, that means it's happening to the x. Okay, so it's happening to the x value. It's going to be backwards from what we think. So remember here, when we subtract, this is going to move it left or right. Because x's are opposite from what we would think, this is actually going to move it right 2 units, which is a horizontal shift. So here I have my transformations written down, HSRV. So I have a horizontal shift that tells me to go right 2. And then to help myself out, since I'm going to be doing this in an XY table, I'm going to go ahead and write myself a little note that in order to go right 2, I'm going to have to add 2 to all my x's. Okay. Now notice that was the only transformation we have, so we don't have stretching, we don't have reflecting, we don't have a vertical shift. So I'm going to go ahead and write up here, now I want to make this look like x minus 2 squared. I'm not going to make its own xy table by plugging in values. What I'm going to do is take the xy table that I already have here, the one in green that's my original, and I'm just going to modify it. To modify it, all I have to do to go right 2 is to add 2 to my x's. So I'm going to take my original x values, and when I rewrite them, I'm going to do my x's plus 2. Oops, not x squared, sorry. I'm going to do my x's plus 2. So -2 plus 2 gives me 0. 0 plus 2 gives me 2. And 2 plus 2 gives me 4. Now notice I did not do anything to the y's. So I'm going to use the same y values that were in my original table. Okay. Now that I have my new function, I'm going to graph these ordered pairs. So at 0, I'm up at 4. At 2, I'm at 0. And at 4, I'm up at 4. So notice when I connect my dots, what happened is that my graph did in fact move to the right 2 units. Okay, so this is my function f of x. Okay. So now using that new function f of x, I'm going to go ahead and determine my domain and range. My domain of my blue picture here goes from -infinity to infinity because it keeps going left and right. My range, my lowest y value on my blue graph is a 0, and then it shoots up to positive infinity. Okay. So this is what I'm looking for on your worksheet homework, is that you identify the parent, you make an XY table for the parent, and then for each transformation, you make a new XY table that you modify each step, okay? And then you graph your completed, the last table, your completed function. Let's look at another one, okay? Here, I'm going to rewrite this because for some reason, anytime this 1 is written out front, it screws people up. So I'm going to rewrite this function as f of x is equal to negative absolute value of x plus 2 plus 1. Okay, so we should easily be able to see that our original parent function was the absolute value of x. So I'm going to go ahead and go down here and make an xy table using the absolute value of x. Okay, I know that the absolute value function should make a v, so I'm going to plug in negative and positive values. On your table of values, as long as you have at least 3 good points that give you a good shape, I'm okay with that. Okay, if you have something like a cubic or something that has a little bit more complicated shape, you might want to use more values. Okay, but 3 is usually the rule of thumb that you need at least 3. So when I plug these in, this just makes them positive. So I'm going to go ahead and graph my points. At -2, I'm up at positive 2. At 0, I'm at 0. At positive 2, I'm at positive 2. Okay, so this is my, excuse me, my original function. So I'm going to go ahead and just label this the absolute value of x. And now I need to see what has happened. Okay, so there's 3 things I notice. The first thing I notice is that I have a plus 2 on the inside. If it's on the inside, it's affecting the x. Okay, so this is going to move it left or right. X's are backwards from what we would think. So since it's a plus 2, this is actually going to move us to the left. Okay, that's a horizontal transformation. So I'm just going to write next to the h, left 2. Now to move it left 2 in my table of values, I'm going to have to subtract 2 from my x's. Okay. Now I want to look at the other ones. The next one I see is this plus 1 out here. If I have a plus 1, notice it's outside the function. The function here is the absolute value. So anything that happens inside that absolute value is being applied to the x. Anything that happens outside the absolute value is happening to the y. So since I'm adding 1 outside, that's going to be a vertical shift. So I'm going to write that next to my v, and that's going to move my picture up 1. To move my picture up 1 in my xy table, I'm going to have to add 1 to my y's. Okay? And then the last transformation I have is this negative out here. Okay? A negative, remember, represents a reflection. So I have to figure out which variable is being negated, and it will flip it across the opposite axis. So here my negative is outside the function. It's outside the the absolute value. So since it's outside, it's being applied to the y. When I negate my y's, it flips it across the x-axis. So I'm going to put this next to r because that's reflection. A reflection about the x-axis. And the way that we get that is by negating the y's. Okay. So now I have my 3 transformations. So that means that I should have 3 xy tables to represent these. So my first one, remember, we do them in HSRV order. So the first thing I do is h, which is my horizontal shift of left 2. So now my function should look like x plus 2 inside my absolute value. Okay. To move it left 2, I look at my little cheater up here. I said I need to subtract 2 from my x's. So I'm taking my x's from my original xy table, and I'm going to subtract 2. So negative 2 minus 2 gives me negative 4. 0 minus 2 gives me negative 2. 2 minus 2 gives me 0. Notice I did not change my y's, so they stay the same. 2, 0, 2. Then I look at my next transformation, which is my reflection. So that means now on my function I have the negative. Okay. To do a reflection about the x-axis, I'm going to negate my y's. So I'm going to use my xy table from the previous step, but this time I'm going to change the y's. So I'm just going to say negate y's. So my x's stay the same, so I'm going to go ahead and write them in, negative 4, negative 2, 0, and I'm just going to change all the signs on my y values. So negative 2, negative 0, which is still just 0, and negative 2. Okay. And I have one more transformation. My last one is to move my picture up 1. So now my function looks the way I need it to be once I add on that plus 1. And to move it up 1, I now just need to add 1 to my y's. So I'm going to do y's plus 1. Again, my x's stay the same from the previous xy table. So negative 4, negative 2, 0. When I add 1 to my y's, negative 2 plus 1 is negative 1. 0 plus 1 is 1. Negative 2 plus 1 is negative 1. Okay, so notice this last xy table is exactly my f of x function. This is how I want it to look. So I'm going to go ahead and graph it so I see what my new function looks like. So at negative 4, I'm at negative 1. At negative 2, I'm at positive 1. And at 0, I'm down at negative 1. So notice my new function is now in blue. This is my f of x. Okay. So what happened, if you start with the green picture and just think through it, we had the green picture and then we went left 2. Once we go left 2, then we flip it down across the x-axis. Okay. So we started out like this, we went left 2, then we flipped it down, and then we went up 1. Okay. And that gives us our blue picture. Okay. So now I want to go ahead and write domain and range. My domain here is negative infinity to infinity because it's going to keep going left and right. And then my range, I start with my lowest y value, which those arrows say they're going to keep going down. So negative infinity up to my highest y value, which in this case is a 1. Okay. So notice I have a table for my original parent function. I have a table for each transformation. I have my graph. And I also have my domain range. Your worksheet looks just like this. So this is what I'm expecting you to do. I'm going to take off points if you don't show each table. Okay. All right. So let me do a couple more and then I'll have y'all work on something. This one, my parent function, is the square root of x. So I'm going to go ahead and make a table for the square root of x and graph it. Now remember, with the square root of x, we can't have negatives. So I'm going to start with 0, 1, and 4. When I take the square root of 0, it's 0. Square root of 1 is 1. Square root of 4 is 2. Okay. Excuse me. So when I graph these, I have 0, 0, 1, 1, 4, 2. Okay. So this is my original square root function. Excuse me. So I'm going to go ahead and label this square root of x. And now I'm going to see what transformations have happened. Notice I have a negative and it's outside the function, which means I'm negating my y's. Remember, negation implies a reflection. If I'm negating my y's, that's going to flip it about the x-axis. So this is a reflection. So next to r, I'm going to say about the x-axis. And what I do in my table of values is I negate my y's. Okay. The next thing I see is that I'm subtracting 1 under the square root. So since it's in the square root, that means it's inside the function, which means it's affecting the x. Okay. When I add or subtract to the x, that moves it side to side. Here, since I'm subtracting and our x's are backwards, this means we're going to go right 1. So next to my h, since it's a horizontal shift, I'm going to say right 1. In my table of values, I would have to add 1 to the x's to get it to move right. Okay. And then the last thing I have is the subtraction of 3. It's outside the square root, which means it's outside the function. If it's outside the function, it's being applied to the y. And when I have a subtraction from the y, that's going to move my picture down 3. So I'm going to need to subtract 3 from the y's in my xy tables. Okay, so let's go ahead and work this out. I have my original, and then I do my transformations in HSRV format. So I do my h first, which is to go right 1. So now my function looks like the square root of x minus 1. Remember, I use the previous table's values. I don't plug in new values each time. So to go right 1, I'm going to add 1 to my x's. So I'm going to take my original x's, 0, 1, 4, and I'm going to do x's plus 1. So that will give me 0 plus 1 is 1, 1 plus 1 is 2, 4 plus 1 is 5. And then my y's stay the same. I didn't change them, they stay the same. The next order of transformation is my reflections, which is about the x-axis. So that puts my negative on my function. Okay. And to tweak or modify my table here, I now need to negate my y's. So going from here to here, I'm going to negate my y's. So my x's stay the same, 1, 2, 5, and my y's, I change their sign. 0 stays 0, 1 becomes negative 1, 2 becomes negative 2. And now I can do my last transformation, which is to move my picture down 3, so I can put my subtraction of 3 on the outside of the function. And to do that, I'm going to take my y values from the last table, and I'm going to subtract 3. So I'm going to do y's minus 3. My x's will stay the same, 1, 2, 5. My y's, when I subtract 3, 0 minus 3 is negative 3. Negative 1 minus 3 is negative 4. And negative 2 minus 3 is negative 5. So I'm going to go ahead and plot the points of my new point, of my new function. So at 1, I'm at negative 3. At 2, I'm at negative 4. And at 5, I'm at negative 5. Okay, so notice when I combine, I get something like this. If you're not sure which way to draw the arrow, start with your original function, which you know looks like this. Okay, and then we went right 1, so now it looks like this. Okay, and we flipped it about the x-axis, so now it's upside down, right? And then we went down 3. Okay, so notice my original is pointing this way. I move it right, still pointing that way. I flip it upside down, still pointing that way, and I move the whole thing down, still pointing to the right. So the right side gets the arrow, the other side is just a solid dot. Okay? Then I identify my domain and range. My domain starts at the x value of 1 and shoots out to the right, so it goes from 1 to infinity. My range, I do my lowest y value, which here it's going to keep going down and down and down, so negative infinity up to my highest y value, which is my dot, which is located at negative 3. Okay. Let me look at one more. All right, this one I'm going to rewrite again with my constant at the end so we don't get confused or frustrated. This is the same as f of x is equal to the absolute value of negative x plus 4 plus 4. Okay. My parent function here is the absolute value of x, which we know is a v. So I'm going to go ahead and make a table of values for the absolute value of x. I'm just going to use negative 2, 0, 2. I use a negative 0 and a positive because I know it makes a v. So I want to use values that give me that v shape. If you want to use negative 5, 0, 5 or negative 1, 0, 1, that's fine. Okay. When I plug them in, I get positive outputs, which is 2, 0, 2. So I'm going to go ahead and plot these points, which when I plot them on my graph, we can clearly see it is a v. Okay, and I'm just going to go ahead and label it. This is the absolute value of x. Okay, then I'm going to identify my transformations. I have 3. Okay, I have this negative here in front of the x. Notice the negative is inside the absolute value. If it's inside the absolute value, that means it's being applied to the x. I'm negating the x's. If I negate the x, that tells me it's going to be a reflection about the y-axis. Okay, so next to my r, I'm going to say a reflection about the y-axis. And the way that we get that in our table of values is to negate the x's. Remember, whichever variable we're negating flips it around the opposite axis. Okay, then I have a plus 4. My plus 4 is also inside my function, so that's going to move me side to side. X's are backwards from what we would think, so since we're adding 4, it's actually going to move it left 4. Okay, so I'm going to move left 4 next to my H, which is my horizontal shift, and in my table of values to move left 4, I would need to subtract 4 from the X's. Okay. And then the last thing I have here is my plus 4. It's outside the absolute value, so it's outside the function, which means it's being applied to the y. When we add 4 to our y's, that moves the whole picture up 4. So next to my vertical shift, I'm going to say up 4. And then in my xy table, that means I'm going to need to add 4 to the y's. Okay, so no stretching on this one. And actually, I don't think I marked this one off. We didn't have any stretching on this one. And these. Okay, you don't have to write HSRV if you can see clearly that you don't have one of the transformations. You can just leave it blank, or you can put a line through it when there's not a specific transformation. Okay, so now that I know what my transformations are, I'm going to modify my XY table. The first modification I do, the transformation, is my horizontal shift to go left 4. So now my function looks like x plus 4 inside the absolute value. To move it left 4, I have to subtract 4 from my x's. So here I'm going to do x's minus 4. Okay, oops, let me rewrite that better. X's minus 4. So negative 2 minus 4 is negative 6. 0 minus 4 is negative 4, and 2 minus 4 is negative 2. My y's stay the same as the previous table because I didn't do anything to them. Okay. My next transformation is to flip it about the the y-axis, which means I need to negate my x's. So now I can go ahead and write in that negative inside my function, and I'm going to negate my x's. So from my previous table, I'm going to use my negative 6, negative 4, negative 2, and I'm going to change those signs, which will give me positive 6, positive 4, positive 2. Again, we're not doing anything to the y's, so they stay 2, 0, 2. And then my last transformation is to move it up 4. To move it up 4, now my function looks like absolute value of negative x plus 4 on the outside, which is my final function. I've done all my transformations, so this is the table I'll graph. Okay, to move it up 4, I'm going to take my y's from the previous table and I'm going to add 4 to each of them. So my x's stay the same, 6, 4, 2. My y's, when I add 4, 2 plus 4 gives me 6, 0 plus 4 gives me 4, and 2 plus 4 gives me 6. So now I can go ahead and plot these points of my final table. So when x is 6, y is 6. Okay. When x is 4, y is 4. Okay. And when x is 2, y is 6. 1, 2, 3, 4, 6. All right. So I can see a good V shape. So I'm going to go ahead and connect them. I'm going to label this one my f of x. So notice if I start with my original V, I'm going to move it left 4, and then I'm going to flip it about the y-axis, okay, which is going to put it over here, right? And then I go up 4. Okay, so we ended up with a good picture. Our domain is going to be negative infinity to infinity because it's going to keep going left and right. My range, I start at my lowest y value, which in this case is 4, and I go up to my highest y value, which this one's going to keep going because of the arrows, which would be positive infinity. Okay? All right, so on the next page, there's 2 for y'all to try. I'll give you some time to work on it, and then we'll go over it. Okay? All right, so on this first one, we have 3 transformations. Our parent function is the square root of x, which is our little half parabola. Okay, the -3 inside the function moves it right 3. The negative outside the function rotates it about the x-axis, which means we negate our y's. And then the +5 on the outside of our function moves it up 5. Okay, so our first one we do is to add 3 to our x's. In our next table, we negate the y's. And then in our last table, we add 5 to our y's. Okay, so when we graph it, we should get a little parabola looking like this. Okay, so the arrow is still pointing to the right. And then our domain on this would be from 3 to infinity and negative infinity to 5. Okay. The next one, same idea. Okay, if you need to, you can rewrite this and put the constant at the end. This is the same as f of x is equal to negative x plus 4 quantity squared minus 3. Okay. So here I have 3 transformations. My original function is the quadratic, which is the x squared, which makes a nice little parabola. Okay. The plus 4 on the inside moves it left 4, which means I need to subtract 4 from my x's. The negative on the inside of the function to my x tells me that I'm rotating about the y-axis, so I'm going to negate my x's. And then the minus 3 outside the function tells me that I'm going to do vertical shift down 3 units. Okay, so I made my original parent table. My next table, I subtract 4 from my x's. Next table, we negate our x's to flip it about the y-axis. And then our last table, we subtract 3 from our y's to move it down. So notice our blue function here is now our new f of x function. Its domain would be from negative infinity to infinity. And our range, the lowest y value is negative 3, and then it goes on up to positive infinity. Okay? All right, I'm going to go ahead and do a few examples of some that have stretching and compressing. I'm not actually going to have you graph it, but we're just going to talk about the different transformations, be able to identify them, and write out what we would do if we were doing the XY tables. Okay, so notice here my quantity has a cube on it, which means that my parent would be the x cubed function, or the cubic function, and my transformations, okay, horizontal, I'm looking for a plus or a minus inside my function, which here I have a minus 4. Horizontal are x's, which means they're backwards, so this is actually going to move us right 4. So if I were doing a table of values, I would have to add 4 to my x's. Okay. Then I look for a stretch or compress. Notice inside here, I'm multiplying by 2. I don't care about the negative because remember, negatives are reflections. So I'm multiplying my x's by 2. So since I'm multiplying my x's, this is going to be a horizontal, either stretch or compress. Okay, here we're multiplying by 2, which is bigger than 1, which in our minds would make us believe it's going to stretch it horizontally. But remember, x's are backwards, so it's actually going to compress it. Okay, so I'm going to say horizontal compress. And the way that we do it backwards, you know how like in our xy tables, if we're adding 2 in the inside of the function, we actually subtract 2 on our xy tables. We do the same thing here. We do the opposite operation. So since it looks like we're multiplying my x's by 2, I'm going to divide them by 2. Or in other words, I'm going to put here, I would multiply the x's by 1/2. Okay, I do the reciprocal because remember, x's are backwards. Okay. Then I look for reflections, which are negatives. I have a negative on my x term, which is inside the function, which means I'm negating x, which is going to reflect it about the y-axis. So this is a reflection about the y-axis. And what I would do in my table of values is negate the x's. Okay. And then the last thing I look for is vertical. Here I have a -7 outside the function, which means that my whole picture goes down 7. So in a table of values, I would subtract 7 from my y's. Okay, so this is the same process. The only thing is I threw in the horizontal compress and showed you what you would do in an XY table if you were going to do that. And we'll do an example here in a minute where we actually work it all out. I just want you to be okay on identifying the transformations that are happening. Let's look at the second one. Second one, I'm going to rewrite it with a constant at the end just because that alleviates a lot of confusion. So this is the same as f of x is equal to negative square root of negative x plus 1 plus 6. So I have 4 different transformations going on here. First thing I need to do is identify my parent, which is the square root of x, which is our little half parabola. Okay, and then I look for horizontal, which means I'm adding or subtracting inside the function. Here I'm adding 1, x's are backwards, so this is actually going to move me left 1. And to move left 1, I would subtract 1 from the x's. Okay, then I look for stretch and compress. Notice I'm not multiplying by a number on the outside of my function. I'm not multiplying my x by a number. So that means we have no stretching, no compressing. Okay. I look for reflections, which are negatives. Here I have a negative outside the function and I have a negative inside the function, which means I have a reflection about the y-axis and about the x. I have both. Okay. So here I'm going to say about the x-axis, which means I would negate my y's, okay, and about the y-axis, which means I would have to negate the x's, okay. So remember, those are on the same order of operation. So if I have both reflections, when you work it out in a table of values, you don't have to do them in one specific order, okay? You can negate the y's and then negate the x's, or you can negate the x's and then negate the y's. Since they're both reflections, the order doesn't matter for those two, okay? And the last thing is vertically, am I adding or subtracting outside the square root? Here I'm adding 6, which is going to move it up 6. So I would add 6 to my y's if I were doing an xy table. Okay. Let's look at one more, and then we'll work one out. Okay. So here, notice x over 3 tends to bother a lot of people. So I'm going to rewrite this as f of x is equal to -4 times. Now, if I want to write this without the x being in a fraction, I can look at the coefficient on my x, which here is a 1, and the bottom number, which is a 3. So this is the same thing as 1/3 x squared minus 8. And then it's a little bit easier to see what's going on. Okay, my parent here, since I have a quantity that's being squared, my parent would be an x squared. Okay, and then I list my transformations. Horizontal, am I adding or subtracting inside the function? So inside my squared quantity, I'm not adding or subtracting, which means that there's no horizontal. Then I look for stretching and compressing. Okay, I do have this 4 outside. Remember, I don't care about the negative because those are reflections. So if I am multiplying by 4 outside my function, that means I'm multiplying my y's. Okay, by a number larger than 1, which is vertically going to stretch my picture. So I have a vertical stretch, which means in my table of values, I would multiply my y's by 4. Remember, y's are not backwards. If it looks like we're multiplying the y's by 4, we multiply the y's by 4. Okay? But then I also am multiplying my x by 1/3. Okay, so here a multiplication implies a stretch or compress. Since it's inside the function, that means it's being applied to the x, so I'm either horizontally stretching it or compressing it. Remember, x's are opposite what we would think. So here, since we're multiplying by 1/3, we would think that would shrink it, but it actually stretches it. So we also have a horizontal stretch. Okay. And in my table of values, remember, we do the opposite. So here, if I'm multiplying by 1/3, I'm actually going to multiply my x's by the reciprocal. So I would multiply the x's by 3. Okay, only on x's do you have to do the opposite operation, okay, or the reciprocal. All right, so I have my vertical stretch, my horizontal stretch. Reflection, I do have a negative. My negative is outside the function, which means it's negating the y's. If it's negating the y's, it's reflecting it around the x-axis. So this is a reflection about the x-axis. And in my table of values, I would negate the y's. Okay. And then vertically, I'm looking for a plus or minus outside the function. Here I have a -8. So that means it's going to move my function down 8. So in a table of values, I would subtract 8 from the y's. Okay? So just being able to identify what are the transformations that are happening. Okay, now we've done these with the parent functions, starting with an XY table that we create for the parent functions and then modifying for each transformation. I want to do the same thing on this next one, but here they give us a picture. Instead of giving us a parent function, they give us a picture. If they give us a picture, we have to come up with the original points, just like we do on our parent, but we just use the points that are already on the graph. So here I'm going to go ahead and identify each point. This first point is -6, 0. Okay, my second point is -5, -6. My third point is -3, -6. I have a point here at the origin, so 0, 0. My point that's the highest is 2, 9. And my last point over here to the right is 5, 0. So these are all my original points. So I'm going to go ahead and instead of saying, you know, my parent function is x squared or whatever, we're just going to use these points. Okay? I'm going to wait just a minute to do my table. I'm going to identify all of my transformations. So I have H, S, R, V. Okay? Horizontal, am I adding or subtracting inside the function? I am. I have a subtraction of 2, which is going to move it right 2, which means I'm going to have to add 2 to my x's when I do my chart. Okay? Then I look for a stretch or compress. Am I multiplying anywhere? I am multiplying. I'm multiplying on the outside of my function, right? I'm multiplying by 1/3. So if I multiply by 1/3 on the outside, that's affecting my y's. So this is going to be a vertical stretch or compress. Since I'm multiplying by a number that is between 0 and 1, this is going to compress it. So this is a vertical compress, and I would have to multiply my y's by 1/3. Okay. Then I look for reflection. Do I have a negative anywhere? I do have a negative. My negative is outside my function, which means I'm negating my y's, which means that this is a reflection about the x-axis. Okay? So I get that by negating the y's. Okay? And then the last thing I look for is vertical. Am I adding or subtracting outside the function? Here I'm adding 4, which is going to move my picture up 4. So I'm going to add 4 to my y's in my table of values. Okay, so now I know all the shifts that need to happen. So I'm going to go ahead and say my original function, or my original points here, okay, which we'll just call f of x, right? My original points, I'm just going to write down all those ordered pairs that I just found. Okay, so I have -6, 0, -5, -6, -3, -6, 0, 0, 2, 9, and 5, 0. Scroll down just a little bit so I have more room. 5, 0. Okay, and now I'm going to do my transformations. So the first thing I need to do is my horizontal shift to move it right 2. So now my function is going to look like f of x minus 2. To move it right 2, I'm going to add 2 to my x's. So I take my x's from the previous table, and I'm going to add 2. So -6 plus 2 is -4. -5 plus 2 is -3. -3 plus 2 is -1. 0 plus 2 is 2. 2 plus 2 is 4. And 5 plus 2 is 7. I didn't do anything to my x's, so I'm just going to leave them the same. Okay, please don't do more than one step per table. Okay, I know some of them are easy to do, but make sure you have one table for each transformation. So the next one is my vertical compress. So I'm going to be doing 1/3 times my function. Okay, which means I'm going to take all my y values and I'm going to multiply them by 1/3. Okay. So my x's stay the same, so I'm going to go ahead and just write those in. -4, -3, -1, 2, 4, and 7. Okay, and I'm going to take my y values, and going into this new table, I'm going to multiply by 1/3. 1/3 times 0 is 0. 1/3 times -6 is -6/3, which is -2. Negative 6 times 1/3, again, is going to be negative 2. 0 times 1/3 is 0. 9 times 1/3 is 9/3, which is 3. And 1/3 times 0 is 0. Okay. So I've done my first two transformations. My third transformation is a reflection about the x-axis. So now I have negative 1/3. Write my function correctly. Negative 1/3 f of x minus 2. Whoops, I forgot my squares. Oh no, I don't have any squares. Okay, so let's go ahead and do this. So now, going from my last table to my new table, all I have to do is take those y values and negate them. In other words, change my signs of my y's. So my x's are still negative 4, negative 3, negative 1, 2, 4, and 7. And I'm going to take all my y's and just change their signs. So I get 0, positive 2, 0, negative 3, and 0. And now I can do my last transformation, which is to move it up 4. So now my function looks like 1/3 f of x minus 2 plus 4. And to move it up 4, all I have to do is add 4 to my y's. So from the y's in my last table, I'm just going to add 4. So my x's are going to stay negative 4, negative 3, negative 1, 2, 4, and 7. And my y's I'm going to add 4. So 0 plus 4 is 4, 2 plus 4 is 6, 2 plus 4 is 6, 0 plus 4 is 4, negative 3 plus 4 is 1, and 0 plus 4 is 4. So I have my final table done. So now I just need to plot those points. So at negative 4, 1, 2, 3, 4, I'm going up 4, 1, 2, 3, 4. At negative 3, I'm up at 6. Okay, at negative 1, I'm up at 6. At 2, I'm up at 4. At 4, I'm at 1. And at 7, I'm at 4. Okay, so hopefully we can tell by our dots how to draw our line. So I'm going to go ahead and connect each of them. And notice if we look from our original picture to this picture, it does look vertically compressed because it's not as long as the original. It's been shrunk, right? We moved it to the right 2. We vertically compressed it. We flipped it around the x-axis, which turned it upside down, and then we moved it up 4. Okay? And then we're going to go ahead and find domain and range. Here we don't have arrows, so you shouldn't have any infinities. This has a set starting point and a set stopping point. So our domain here is our x value furthest to the left, which in this case is going to be negative 4. And then it goes all the way to our x value that's furthest to the right, which is 7. Okay. Our range, same thing. Our lowest y value here is positive 1. Our highest y value is 6. Okay. All right, so there's one last one for y'all to try. I'll give you a few minutes and then we'll go over it. Okay. All right. So on this one, we take our original picture that they gave us and identify the points on it, which here are negative 4, 0, 0, 4, and 4, 0. So I went ahead and put my table of values here in green from my original f of x function, and then we look and see what transformations have happened. The negative inside negates my x, which flips it about my y. So that's my reflection. The negative 3 on the outside is being applied to the y. When I subtract 3 from my y's, that moves my picture down 3. Okay, so I go ahead and do it in my table of values. My first table, I negate my x's, so I just change all the signs of my x's. And then going from my first blue table to my second blue table, I then subtract 3 from my y's to move my picture down 3. Okay, so when I graph my finished function here, my circle has been flipped around the y-axis, which in this case really didn't do anything, right? If I take a semicircle and I flip it around, still looks like a semicircle. Okay? And then I move it down 3. So here my domain would be negative 4 to 4, and my range would be negative 3 to 1. Okay, that's the end of this section, so you should now be able to complete your E2.5. There's an assignment on My Math Lab and an assignment that is a worksheet. Make sure on the worksheet you're writing out each transformation, you're showing me a table of values for each transformation, and you're giving me the domain and range. There is a typo where it asks for an asymptote. Okay, we haven't done asymptotes yet, so on your worksheet where it says asymptote, you can just mark that out. Okay. The other thing I wanted to touch on is that the homework for this section, there are some multiple choice ones. I understand that you can solve them using the process of elimination. However, I encourage you to work through each problem the way I've shown so that you'll be prepared to do that on a test and on the final. Okay. If you have any problems, please let me know.